Have you ever pondered the relevance of linear equations in the realm of artificial intelligence? The realm of AI is vast and complex, but at its heart lie some fundamental mathematical principles, such as linear equations. These seemingly simple mathematical constructs are the backbone of many advanced AI algorithms, playing a pivotal role in driving the intelligence behind the artificial. Linear equations form systems, and these systems can represent a multitude of scenarios, from predicting stock prices to programming self-driving cars. They are the keys that unlock the door to understanding the world in a quantifiable way. They help us formulate relationships between variables, enabling us to make predictions and optimize solutions. In this journey, we'll unravel the mystery of linear equations, delve into Gaussian elimination, explore matrix representation, and finally, unearth the solutions of linear systems. We'll also look at how these concepts are applied in AI, specifically in regression and optimization. So buckle up as we explore the intriguing world of linear equations and their role in AI. Embarking on our journey, we first encounter Gaussian elimination. Gaussian elimination, named after the mathematician Carl Friedrich Gauss, is a method used for solving systems of linear equations. It's like a magic trick that simplifies complex problems into simpler ones, making them easier to solve. Imagine a tangled ball of yarn. Trying to unravel it all at once can be quite a challenge, right? Gaussian elimination works similarly. It unravels the knotty system of equations, one equation at a time, until it becomes a streamlined, manageable task. So, how does it work? The process involves three types of row operations: swapping two rows, multiplying a row by a non-zero number, and adding a multiple of one row to another row. By performing these operations, we aim to transform the system into what we call row echelon form. In this form, the system is much easier to solve, just like our untangled ball of yarn. Think of it as a game of chess. Each move or operation must be strategic to keep the game or system under control. The goal is to checkmate the king, or in our case, find the solution to the system. Now you might be wondering, why Gaussian elimination? Why not just solve the system as it is? Well, that's like asking why we use a map. Sure, you could reach your destination without one, but it would be far more difficult and time-consuming. Gaussian elimination is our map, guiding us through the labyrinth of linear equations. It's particularly important in the world of artificial intelligence. AI often deals with large data sets, which can be represented as systems of linear equations. Gaussian elimination helps us reduce these massive systems into a more manageable form, allowing for faster and more efficient computation. So you see, Gaussian elimination is a powerful tool that helps us untangle the complex web of linear equations. It's like having a secret weapon in our AI arsenal, enabling us to tackle even the most complicated problems with relative ease. Having mastered Gaussian elimination, we now venture into the territory of matrix representation. Matrix representation is a method of expressing systems of linear equations in a compact, organized manner. It's like a neatly packed suitcase where every item has its place, making it easier to carry and understand. In this case, each item is an equation, and the suitcase is the matrix. In the realm of linear equations, matrices are a Swiss Army knife. They help us simplify and streamline our work by providing a consistent and efficient structure. Each row in a matrix represents an equation, and each column stands for a variable. This arrangement creates a grid of coefficients, a numerical snapshot of our system of equations, if you will. But what makes matrix representation such a game changer? It's all about efficiency and simplicity. Imagine having to solve a system of 5, 10, or even 20 linear equations. Writing them out individually would be quite a task, wouldn't it? And that's where matrices come into play. They allow us to condense all that information into a neat, compact form. It's like folding a map to only show the section you need. Moreover, matrix representation paves the way for matrix operations such as addition, subtraction, and multiplication. These operations parallel the ones we perform on equations, but are executed in a streamlined fashion. They are the nuts and bolts that hold our linear system together, enabling us to manipulate and solve it more efficiently. Finally, matrices have a secret weapon: determinants. Determinants are special values derived from matrices. They act as gatekeepers, telling us whether a system of linear equations has a unique solution, no solution, or infinite solutions. With this information, we can strategically navigate our way through the system of equations. Matrix representation, therefore, not only simplifies but also streamlines our interaction with linear equations. We've unpacked the suitcase and now we're ready to explore further. So let's move on to the next exciting chapter, unveiling solutions of linear systems. Now that we have a grip on matrix representation, let's delve into the solutions of linear systems. There are three types of solutions that a system of linear equations can have: unique, no solution, and infinite solutions. Each of these outcomes tells us something different about our system, and understanding them can be incredibly useful. First, let's talk about unique solutions. This is the case when our system of linear equations has exactly one set of values that satisfy all the equations. Imagine you're trying to solve a puzzle, and you find that there's only one way all the pieces can fit together. That's what we mean by a unique solution. It's a clear, definitive answer, and it's what we're usually hoping for when we're working with a system of linear equations. But life isn't always so straightforward. Sometimes we find that our system has no solution. This happens when the equations are inconsistent with each other, and there's no possible set of values that can satisfy all of them at once. It's as if you're trying to solve a puzzle, but you realize that some of the pieces just can't fit together, no matter how you arrange them. When you encounter a system with no solution, it's a signal that there might be an error or inconsistency in your data or model. And then there are times when our system has infinite solutions. This is when there are infinitely many sets of values that can satisfy all the equations. It's like having a puzzle where there are countless ways the pieces can fit together. In terms of linear systems, this usually happens when the equations in the system are dependent on each other. While this might seem overwhelming, it also opens up a world of possibilities and can be particularly useful in scenarios where flexibility and adaptability are key. So there you have it, the three types of solutions in a system of linear equations: unique, no solution, and infinite solutions. Each offers a different perspective, a different story to tell, and understanding them is crucial in the world of AI. Understanding these solutions equips us with the knowledge to predict and interpret the behavior of our AI models. Armed with this knowledge, we now turn our attention to its applications in AI, specifically regression and optimization. Regression and optimization are two areas where our understanding of linear equations, Gaussian elimination, and matrix representation truly shines. They're the engines that drive AI's ability to learn, predict, and make decisions. Let's start with regression analysis. This is a statistical method used to examine the relationship between two or more variables. In the context of AI, regression analysis helps in predicting continuous outcomes. For instance, predicting the price of a house based on various parameters like its size, location, or age. Here, linear equations are the backbone, allowing us to establish relationships between variables, while Gaussian elimination and matrix representation aid in handling the complex calculations. On the other side of the coin, we have optimization. This is the process of making something as effective or functional as possible. In AI, optimization algorithms are used to fine-tune models, improving their performance and accuracy. These algorithms often involve finding the minimum or maximum of a function, which is where our understanding of solutions of linear systems comes into play. They help determine the optimal weights and biases for AI models, enabling them to make more accurate predictions. The beauty of these concepts lies in their versatility. Regression can be used in everything from financial forecasting to healthcare predictions, while optimization plays a crucial role in areas like logistics, scheduling, and even game theory. These are not just abstract mathematical concepts. They're tools that allow AI to solve real-world problems, making our lives easier and more efficient. In essence, the principles of linear equations, Gaussian elimination, matrix representation, and solutions of linear systems are not just theoretical constructs. They are the very building blocks that enable AI to learn from data, make predictions, and continually improve its performance. We've seen how these mathematical concepts come to life in AI, driving critical computations and enabling sophisticated predictions. We've traversed the landscape of linear equations, from Gaussian elimination to AI applications. We've seen the magic of Gaussian elimination simplifying systems of linear equations, and the elegance of matrix representation in managing these systems. We've explored the various solutions these systems can offer, unique, none, or infinite, each with its own implications. In the realm of AI, we touched on how linear equations play pivotal roles in regression and optimization, two key techniques that enable machines to learn from data and make informed decisions. Regression helps predict future outcomes, while optimization aids in finding the best possible solution for a given problem. This journey has been about more than just math. It's about understanding the fundamental building blocks that make AI what it is today. And with that, we appreciate how linear equations form the backbone of AI, powering its capabilities and expanding its potential.